Okay, so today is a kind of special seminar. I'm not presenting new theory or anything like this. I just want to review how pyTAGI works. One of the reasons is that many of us will have to make some modification. We'll have to open the code and either add layer, modify layer, or just understand how it works, debug, or try to troubleshoot what's going on. And I have to do it myself. And at first, when I look at the code. So TGI is super fast if you experience with it. If you run it, it works well. But the first time you open the code, it looks a bit like this. Okay. And what I want with this presentation is to kind of untangle so that afterwards you see all the kind of structure and the cleanliness into it, not just these lines of code that at first don't mean much. Why they don't mean much is because this is theoretically the update equation that we can see in the TGI paper. And when you look in the code, it doesn't necessarily look like this. Okay, theoretically it's the same, but it doesn't translate one-to-one to what is there. And all of this has been made initially for efficiency. Okay, so, and it's everywhere the same along the code. So I want to look out as the backward step, the one that is used to make inference either from hidden states or parameter, how is it made? So hopefully at the end, it's gonna look like this. So I'm gonna make the presentation around the linear layer, the feed-forward fully connected one, just because it's the classic one that is easy to understand, but all the layers are structured in the same way. So just as a reminder, we always see the same thing, but it's all never to have a refresher. So we're going to say X is the input layer for just a simple MLP. We're going to add activation units, which are nonlinear transformation of what we're going to call Z hidden units. So sigmoid could be any activation function. In this case, we're mostly going to use ReLU, but it could be anything. So in these kinds of graph, hidden units and activation units are overlaid on top of each other. And to go from one hidden unit, one layer of activated units to a subsequent layer of hidden units, we are going to say we're going to multiply by weights, we're going to add a bias, and we're going to sum all these products together to get Z1 on the subsequent layer. We're going to have the output layer, and we're going to have Y, which is the observation, where typically Y is going to be Z output plus some observation error. Okay, a zero mean Gaussian random variable. So Y are my observations, and in this case, the parameters are going to be the weights and biases. And in this presentation, we're not going to represent all of these connections. We're going to use this kind of graph representation where each node represents a layer, and the arrows represent all the parameters that are involved in going from layer to layer. Okay, again, a slide about TGI theory. So in a MLP or actually in any architecture, it always works the same way. So once we define the structure to go forward, the inference or the parameter or hidden state inference, the Gaussian estimation, or the Gaussian update, is made using the assumption of conditional independence between subsequent layers. So what does it mean? It means that the layer, say Z1, is conditionally independent upon Z3 given Z2. Okay, this is not fully right with ResNet. We're going to come back to this in a subsequent seminar. But for normal like feed-forward connection, feed-forward neural networks such as a linear layer like this, it holds. So what does it allow us to do is to go, so if I want to infer from my observed value what should be the posterior for my output layer, I use the classic Gaussian conditional equation. This is all standard stuff in the TGI paper. Then if I want to go from the posterior for Z output, update the parameter connecting into that layer, I'm going to use not anymore the Gaussian conditional, but the RTS, the equivalent of the smoothing equation that we have in the Kalman filter. Where here we're going to make a slight modification in the notation. So talking about the layer with their specific indexes J and J plus for referring to a specific layer, we're always going to look at everything in pairs. Okay, so the current pair we're trying to update is no superscript. And the next one in the loop, so the one we try to pull information from, is the z plus. Okay, we update the one without superscript from the posterior we've updated previously on the following layer. So the plus is the one that is the as the updated information. The one without superscript, the one we're trying to currently update. So it changes slightly the notation to this one, where this is the posterior we've already updated for the output, and this one is the one we're trying to update. And, oh, sorry, no, it's not exactly. This is the previous one we've already updated, and this is the prior for the same quantity before updating. So that represents that quantity that has just been updated from the data. J here is not exactly a Jacobian. We call it the J matrix, but this is what we have here on the bottom. And it's the same J quantity for updating the expected value and the covariance matrix. Okay. We have the same thing now if we want to go to update not the parameter, but to update from hidden layer to hidden layer. Okay, the equations are almost the same, except that instead of being the covariance between theta and z plus, the parameter and the parameter where we want the fetch information from, it's the covariance between the layer we want to update and the layer we want to fetch information from. Okay. But what we have to see and where I want to come up to is that we have this recursive procedure. Okay, we're always going to define a structure in a sequential way so that when we want to do the updating to update or posterior information for each layer, we're always going to do this from the subsequent layer. So whatever is z plus here to update z, once we have updated this quantity, it becomes z plus to update that layer connected into it. And it's always used in a recurrent way like this until reaching the input. Okay, so now let's take a second look at the hidden state update equations. Let's imagine we have two subsequent fully connected layers. So A are going to be the activated unit for one layer, and the subsequent hidden unit Z plus. Okay, so in that case, these are the same equation we saw previously. So first thing we do, we're going to replace the J by this explicit thing because we're going to start to manipulate those equations. And in TAGI, the update is always done from Z to Z. So we're skipping the activation unit A that we add previously here, okay? It's implicitly there. We can marginalize over it. The updated equations are made such as it's always Z to Z. And this is not something that we needed to do. It's a choice. We could have updated from A to A, no problem. Or we could have updated from Z plus to A to Z, but it's more efficient just to do it from either A to A or Z to Z. In our case, we chose Z to Z. So these are the resulting equation to go from hidden layers to hidden layers connected into it. And right now, we're going to focus our attention on not the covariance updating, but only the expected value updating. Because once we understand what's going on there, it's really entirely analogous for what's going on with the covariance update. So let's remove the covariance update for now. Let's only look at the expected value where we directly replace that J in here, the covariance of ZZ plus, times the inverse of the prior variance for the next layer. We have that difference term here, same as before. So here, if we transform this, because this was the kind of multivariate case for updating all the hidden layer at once, let's simplify further this by saying we want to update just one hidden state, just that ith hidden states from the information coming from all the subsequent layers. Okay, in that case, it's simplified to this. So now we have only one quantity that we're going to output, the posterior mean or Zi. So we have the prior mean for Zi. We have the covariance between Zi and that subsequent hidden layer. So now that term is now a vector. What's this? We have a vector. This is the vector representing the variance of what we have here. We can represent it as a vector because we assume in TAGI that everything is diagonal covariance matrices. Okay, so now instead of representing it as a matrix, I can do an element-wise operation with my O dot here, and I multiply by the inverse of the vector of my variance. And this term is the same as usual. Okay. And If we expand what was that covariance between Zi and Zi plus, we obtain this formulation. Okay, let's look in detail at where does it come from. The covariance between Zi and the subsequent hidden layer can be broken down as the covariance between Zi and Zj plus. Okay, we're just going to look at one term. Where does it come from? How do we get this? What is the basic building block to obtain what is going to be that covariance between Zi and Zj plus? What's in Zj plus?
We have the information from the activation function.
We can have the information from yes. What else? How do we go in an MLP? How do we go from layer to layer?
Weight bias. Yeah.
Weight and biases. Okay. So what is the equation theoretically? We're going to multiply Ci by a weight.
Yeah. By the activation.
And we're going to same all of it. But if we look at just a pair, to go from Zi to say Z2 plus, it's going to be Zi times true inactivation function is going to be AI, and I'm going to multiply that AI by a weight. Okay, so the contribution of Zi, it's only this. Go through an activation function AI, and then I multiply by a weight. So in this case, I need to look at what is going to be the covariance between Zi and WGA AI. So WGA is coming from Zi going to Z plus J. Okay, and AI is the transformation of Zi. And how do we explicitly find what is the formulation of that covariance?
GMA.
GMA equations, exactly. So whenever we don't know, we say GMA equation. So we have the product term here, and it's going to be the covariance between the product term and a single variable. It's going to boil down to these terms. So we're going to have covariance of Zi and the weight times the mean of my second term. We're going to have the covariance between Ci and AI and the mean of my first term. Okay? Covariance Zi Wij. What do we have?
0.
0, because we assume in TAGI that the weights are independent from the hidden units. So we're going to get 0. Covariance between Zi and AI.
Phi.
Phi.
CDF for.
Almost. You're on the right track, but it's not exactly it.
I mean, is the sigma is the variance of standard deviation of Z multiplied by.
Is going to be the variance of Z?
The variance.
Multiplied by the Jacobian of the activation function going from A to Z. Okay, so it's going to be the variance of my Zi times dAI dZi. Okay, so this term is 0, as you said. So in that right-hand term, it is non-zero. I'm going to have the mean of Wij times dAI dZj, the Jacobian of my activation function, times the variance of Zi. So this is what explains my covariance term that I have here. Okay, so this was exactly business as usual what we had previously. We needed to multiply by the covariance that we explicitly represented as this. Okay, so this is the same equation I just showed you. Okay, now we're going to see what is the correspondence between that equation that is the theoretical update equation and what is the code in pyTAGI. Okay, now I'm only looking at the code in C++ implementation, but in CUDA it's the same thing. It's analogous. It's the same strategy that's used. So in the CVP file linear layer, you're gonna have the backward function. I forgot. Is it the function? Is it the method? How should I call backward? Method. So that we have the backward method, and is it the method as well? The linear backward XC delta is it the method as well?
That's a function that is.
Okay.
What's the difference? I don't understand.
I don't understand either.
It's part of the class. Yes.
Yes, so that's it.
Right.
So
I mean, a function part of a class will be a method, right?
Yeah.
And then if it's alone, it's gonna be a
Yeah,
function.
this function is all
Okay.
used for that.
So this is still all Tango in my mind, but basically, in the backward method, we have the linear backward delta function that's called, and that is supposed to do this operation, along with the same thing with the variance. But right now, focus on the expected value, because if we understand the expected value, variance is the same thing. So this is the code that we have in that linear backward FC delta Z. Okay, NI input size, NO output size, not super important for now. This is because we can operate over batches of data. So it extract the row and column indices, not super important for us right now. We initialize those two variables to 0, not super important. What matters for us is what we have in that for loop. Okay, we go from I equals 0 till the number of output. So we start with our 0 value, sorry, we have 0 value sum mu z, and we're going to add delta mu, and be careful, delta mu is not this quantity. Delta mu is this quantity pre-multiplied by the inverse of the variance of z plus. Okay, so delta mu is the input to this function. So we're going to take that input of the function, we're going to multiply it by mu w. Okay, this is what we have here. And we need to sum over all the output, because remember, when we want to update one hidden unit, we need to take into account the information coming from all the output into that initial hidden unit. Okay, so this is why we operate over I from 0 to number of output, to take account into information coming from all the output by multiplying by the corresponding output weights. Okay, once we've finished this loop, I gray out, but these were the computation for the variance. We have this accumulated sum that is multiplied by the Jacobian TAGI. So the mu w is the what we have here. The delta mu is the input. Jacobian is what we have here. Okay, but what is striking is that this is done. This is the output, delta mu z. And we have never multiplied by sigma z, and we have never divided by sigma z. And this is the key strategy. Okay, by avoiding to multiply, it's like if your next result for the subsequent layer is already pre-divided. Okay, and that makes it super efficient. So if we look at just this equation, and we're gonna further look at this, so I just remove the code and I send this mu z the left-hand side of the equation. This is what I have. So I have a delta plus term here on the right-hand side. I have a delta on the left-hand side. I can further divide by this sigma zi square on this side. So what you see is that what was initially my input, delta mu, I now have on the left-hand term the same thing, same delta mu, but for the subsequent layer I'm going to use in my next update step. So the output of the update is delta mu z. So it means that the delta mu z that I have on the right-hand side of my equation is equal to what's going to become my delta mu for the next subsequent layer in my update step. And by avoiding to multiply by the term sigma zi, I don't need to always divide here. And this is particularly efficient because that term delta mu is everywhere. Okay, if we look at the TAGI equation, these are the RTS update equations for the hidden states and for the parameters. Okay, and what we can see is that if we directly plug in the J term in all of our equations and J theta here, we're going to get these equations. And these equations, we can see that what we have here is a function of delta mu. We have a function of delta mu on the parameter update as well. We have a parameter here for the variance. So we're going to have a delta var, delta var. And these are the same for both the parameter and the hidden states. So in pyTAGI, these quantities are directly the delta mu and delta var that are passed along from layer to layer in the backward step that we do in a recursive way. And then the only thing we need to compute to make an update for a specific layer is what is going to be those covariances, sigma z plus and sigma theta z plus. Because the delta mu, delta var are always the same thing. Okay, so let's look at how would we do this? How would we compute delta sigma theta z for updating the parameters? So in that case, let's assume that the parameter theta we want to update is a weight. Okay, how would I find what is my covariance between a weight and my subsequent layer z plus?
GMA.
Okay, but it's going to be a covariance between what and what? So before it was z and WA. Now it's the covariance between what and what that I'll need to look for.
WW and WB.
Nope.
So Z plus is WZ.
WA.
Ah, yeah. It's between W and WA.
W and WA. How do I obtain this term?
GMA.
GMA. So if I do the same thing we had before, it's always the same structure. Covariance between W and W is going to be the variance of W minus mu A. And the covariance of W and A, like before, it was 0. This term drops. I'm just going to have the variance of W times mu A. So it means that sigma of WZ is going to be this term. So I should get that formulation that is implemented in pyTAGI for updating the weight parameters. Okay, let's look what we have. So this is the code we have. I again grayed out the code for the variance, but it's really the same strategy. So we're gonna have that delta mu, which is that pre-divided term because we didn't multiply in the previous layer. So that delta mu times mu a. So perfect. And in this case, there's something special. You see mu ai index b, because typically when we compute, we're going to compute with a batch of observations. So hidden units are independent of batches because each item in a batch will have its own hidden unit values. But when we update, we want to take all the hidden layers and update a same weight with all the batches of data. Okay, so they will all contribute. So that's why here I have a loop over I, which is the batch index. Okay, because we want to update mu W from all the observation in my batch. So basically what I'm going to do is I'm going to multiply that delta mu by the mu A from all the element within the batch B. And once I've done this, I'm simply going to multiply by bar W. So what I have here. Okay, and at the end, that product of the two is going to give my delta mu W, which is going to be the output for the backward for updating the weights. Okay, so this is how it works. So the last thing I want to cover with you is how can we apply the same thing for the output layer? The output layer doesn't use the RTS equations. It's going to use the Gaussian conditional that looks like this, that are slightly different. So it's not the difference between the updated value and the prior, it's the observation and the mean. And then here it's going to be the prior covariance for the predicted observations. So now if we say what is going to be sigma y z output, what is going to be that covariance, typically for NLP? So the covariance between my observed value and the output of my neural net.
The observation are
Sigma.
no.
Wow. Sigma Y.
So if we reverse the problem, what is sigma y?
Sigma Y is sigma Z plus
Sigma
sigma V.
output plus sigma v, the observation error plus the variance of my output layer. Perfect. So given this formulation, what is the covariance between sigma y and between y and z output? So keep in mind the covariance is the common part of the variance that is shared by both y and z output.
of the Z output.
Variance of the Z output, because since the observation error is independent of Z output, it's not shared among the two. So the only part here is going to be the variance of Z output. Here, there's a little trick in pyTAGI, because in the standard way, the output layer is not passed through an activation function. But it could be in some special case. So pyTAGI is made such that the Z output could be passed if needed in an activation function. In such a case, to get covariance between YZ, it would be actually covariance between YA. And in that case, we would need to multiply that sigma Z by the Jacobian of the activation function. So basically, dA dZ. So sigma Y, as we said, is going to be the covariance of Z output plus covariance of V. Covariance of Z output, if we use an activation function, is going to be instead covariance of A. Okay, but this is just in a case where we use an activation function. If we have no activation function, it's just going to be a linear function, and the derivative is going to be 1.
In the case of the when we pass it through for the TAGI through the exponential activation function, does that apply?
Because in the TGIV, we're going to have the normal output layer that's going to be doubled down to have the V2 bar corresponding with each output. And what you want is that your normal output hidden units are passed through a linear activation function. The other one are passed through an exponential.
Yeah.
So yes, it would apply there. So you would need the Jacobian that is 1 for all the normal output unit, that is exponential for the other ones. Is this what you have implemented?
Oh, I don't know.
But technically,
I think so.
that's a case where it would apply, where you need your output layer to be passed into an activation function. So the first part of the hidden units are untransformed, are passed through the linear activation function, which doesn't change anything.
Yes.
And the other ones are passed through, in your case, an exponential activation function. And it's taken into account in here. Make sense?
Yeah.
But then if we replace those terms in the same formulation we already have, we're going to say that the covariance here, I forgot something, this should be -1. Okay, the inverse of the sum of these two. This is the inverse of sigma y. We have here the term sigma yz, which is going to be the product of these two, where this can account for the fact we have an activation function. So here, if we look at all this term that we have, which is the Jacobian, the inverse of sigma y, and the difference between the observed value and the prior mean, is that delta that's going to be passed along to the next layer. And again, notice how we don't multiply by sigma z. While the variance is the same, we didn't look at the variance, but it's the same. We have 2 times the sigma z if we don't multiply. This is going to be that delta bar.
We take the Jacobian AZ, but it's the transpose is on the.
Yeah, no, I probably mess up the thing. It's still like
Okay.
So we need to distribute and change that transpose.
Yeah.
But the terms that are regrouped into what's going to be delta mu are these terms here. Okay. So let's look at this. If we go in the file output layer CPU.cpp, this is where we're going to call everything. So if we go at output layer CPP, so you see this is a file with a lot of old stuff that has been commented, but if we go here, update output delta Z. Okay, compute delta Z output. So we're going to go in base output updater, and this is where we're going to compute the delta Z outputs. Okay, so what we have, we're going to have here at temporary variables is going to be the Jacobian divided by var A plus var ups. So this is sigma V, this is sigma A. So these should be inverted. So this is why we have Jacobian divided, because these two, this is Jacobian times sigma y inverse. So perfect. This is if we have none, if we have a missing value, so we do nothing. Otherwise, we're going to multiply that division between the Jacobian and sigma y by the difference between the observed value and mu a versus for the delta var is directly going to be times the Jacobian. Okay, so this is basically how it works. The same thing for linear layer. If we go in the linear layer, you can see here we have things for the forward. We're going to go and we're going to find the backward, and we're going to see if we can find our way as well. So where do we have the backward? Forward, we have the backward. Okay, so you see that in the backward, what it does is going to make, if we have multi-thread, this chunk, if we have a single thread, it's going to be this one. So linear backward FC delta. We're going to go there. It's going to be the same code that we've already seen. Okay, so this is basically how the backward works, and it's the same across all layers. Always the same strategy. It's always boiled down to finding what is that cross covariance between the different hidden layers. So I'm going to finish on this. I've done a tremendous work in doing this, and this implementation is fast and it's crazy well made. It's really clever, all the tricks are done. And what I've presented here is just the tip of the iceberg, in a sense where it's not what I've presented today that makes pyTAGI pass. There are way more things in this that are involved in the back-end optimization, the kernel optimization to make. This is part of it, but this is just a tiny part. So we have plenty of material to cover in the next seminar to really like uncover all the things that makes pyTAGI fast and efficient. And I want to acknowledge Dai's contribution because I had to ask him twice to explain me how does this work to really get my head around it. So thanks, Dai. That's it.
Okay.
Questions, comments about this? Do you guys mostly get it? It took me a long time to get. It was 45 minutes.
Now with the presentation, I feel it's really like if we go into the code, it's gonna be much clearer to understand.
Yeah,
what's
and I think it's going to be relevant because if any of you implement anything or verify or anything, this is really going to be what you're going to be facing in most of the layer.
For me, I understand maths, but the code is.
out of my knowledge.
And this is related to what we were discussing yesterday with the ResNet block, which is the same thing. It's always boiled down to looking at what is going to be the covariance term. I spent the whole day yesterday finishing the presentation. I thought I really understood, and then I couldn't get ResNet to work. And finally, with God's help, I got ResNet to work. But
Is ResNet working?
it's not working yet. But to the understanding of how is it implemented, it's implemented the same way. But once you look at ResNet, you realize that doing nothing is the right way to do. So it looks like there's no update equation, but it's because the covariance here involves nothing but this. So basically it disappears, like you can just skip the update connection and directly pass along the delta mu delta var. Okay, except that there's a Jacobian, but that comes in the later step. But in the main step of updating, you can directly just pass along these quantities. And it looks like something is missing. It's not missing, it's just that you don't need to do anything, so I didn't do anything.
So the Jacobian, it's
The Jacobian needs to be done in the subsequent step. It's still missing.
but it's not done.
It's not done yet, but it needs to be done. The person that is passed should be passed along in the way it's currently done. We just missed one step, or we're going to multiply the final result, where we sum both contribution from the skip step and from the main block update. After summing the two delta mu delta var, we multiply these quantities by Jacobian. Okay. That's it.
Nice.